Welcome to System Devices 1, Week 4 review, what you should know by the end of the week. So in this week's lecture we were looking at sequential logic, so flip-flops, memory cells in our system. So in particular we're looking at the internal registers that we have inside our processor that we will be building, and its external memory, its SRAM here. So introduced the ideas of what a flip-flop is by this kind of simple SR flip-flop, so set reset flip-flop. Basically a circuit can remember one bit, so our output Q here can be set to a logical 1 by pulsing the set line, or reset to a logical 0 by pulsing the reset line. But the key point to remember here is that flip-flops have state, they remember previous values. And obviously we don't see that with combinatorial logic, so you put an input in, you generate an output, remove that input, obviously the output will go to a different value, and that's the key difference. So within our processor we've got three main memory elements. We've got an instruction register, an accumulator and a program counter, and we'll be looking at those in a lot more detail in the next set of lecture slides where we actually put all these things together to build our processor. So a key building block of those memory elements, those registers, are D-type flip-flops, and we'll be using those in our designs. Don't worry too much about the low-level transistor implementation. I'm solely showing that here just to show that there's a link back to what we were saying previously, that at the end of the day everything is made out of logic gates, everything is made out of transistors. So this is the internal guts of our D-type flip-flop. So if you want to store binary values inside a system, we need to have arrays of these flip-flops, these single bit storage elements. So if you want to store 4 bits, I need 4 flip-flops, and we looked at our register in this example here. Now another key building block in our system is the program counter, a piece of hardware that stores a count value that you can increment, or you can load it with a particular value. Now, fingers crossed, touch wood, this now should make sense. So in the previous lectures, what we've done, we've kind of identified these building blocks. So the first one we looked at was our multiplexer, then we looked at our adder circuit, and now if we combine that with a memory element, hopefully you can see how we can make a loadable counter. Also, as discussed previously, binary, as in a base 2 representation, is not the only binary representation, so we can represent other values within our system using one-hot encoding, and we do exactly that inside the control logic. And for that we'll be using a ring counter, as discussed here. So a key point to highlight here is that now you know all the key building blocks in our system. So you know how a register will be made, a memory element within the system. You know how the ALU is implemented, because we've built that one up in the labs this week, and the multiplexers we've seen, and the encoder-decoder circuits we have also seen in previous labs and lectures. So you have all the building blocks you need to build our system, and that's what we'll be looking at next in the next set of lecture slides. But before we get to that one, let's have a quick look at how memory is built, just to show you that it is different to internal memory. So external memory uses different memory technologies to save space, to save costs. So we have a quick look at SRAM cells and see their advantages and disadvantages. Next we have the lab, so we'll be looking at our ALU, so how do we implement our adder, subtractor and multiplier within that one. So again, we're using Xilinx. We'll be building up our component using that hierarchical approach. So we're starting at the bottom, we'll implement a schematic using a half adder, then we'll be using 2 of those within a new schematic, the full adder schematic. We look at how we edit the symbols, so do have a look at this one, make sure you're happy moving pins around, editing your symbols. You probably have to do that one later on in the open assessment depending on your solution. Then as always we can simulate that using iSim, so we'll be looking at the inputs coming from the test bench, obviously that A, B and C in, and looking at the outputs coming from your schematic, from your full adder, using sum and C out. We can then use 3 full adders to make a ripple adder, and a key bit here is the idea of buses. So do make sure you're happy about how you use buses, how you can define input ports. So here we've got input bus A, and obviously it's 3 bits. Then using bus taps we can link those off to individual signals within our schematic. So what that process is then discussed going through there, so do make sure you go through that one as a key bit, and again just to kind of hammer that one home, the difference between individual pins coming in, so signals, 1s and 0s, and again buses. Now we have components that can process bigger words. And again we can test that one in iSim, so do make sure you're happy about the difference between signals coming in and buses coming in. So here you can see C in is a signal, so you can see that our single bit wires as we have previously, and A and B are buses because they've got this bigger rectangular shape. X's indicate where you have a transition on a bus, so we're going from the value 0 to 1 to 2 to 3 going through, and you can see it is performing the addition process. So here we've got 1 plus 1 gives me 2. In the lab we combined our ripple adder now with our 7-segment decoder, which we designed in the previous lab, and now we can use that to update the displays on our FPGA board. So now we have 1 plus 1 gives me 2. Bit of a quiz here, obviously this is right, this is not a mistake. 5 plus 4 does equal 11, so make sure you're happy why that is so. Remember, it's an octal calculator. Then we can use the adder to do subtraction by the method of complements. So in the previous lecture we used an exclusive OR. Just to mix things around a bit, we're going to use an array of NOT gates now to implement our inversion and combine that with a multiplexer to make our adder subtractor. So now we have the value coming in. So if we want to do addition, we select the top line, and if we want to do subtraction, we select the second input of our multiplexer, invert the values coming in through the NOT gate circuit, and then add 1, as always, via the carry in. So if the mode line is 0, we'll do an add, and if the mode line is 1, we will do a subtract. So again, our multiplexer is multiplexing buses now, so 3-bit values, so each bit is multiplexed by a bit multiplexer, so that's what's inside that multiplexer component. We could download the schematic and test it out. Again, simulate it here, so again, cin is our select line, so when it's 0 we're doing add, so you can see here 2 plus 1 gives me 3, and when it's a 1 we're doing subtraction, so 2 minus 1 gives me 1. Again, download that one onto our virtual bug trap, so we've got 2 plus 1 gives me 3 if I'm in add mode, and 2 minus 1 does equal 11 when I'm in subtract mode. So again, do ponder why that is so. And in this case it's not because we're in base 8, it's to do with how the digits are wired up, so do look at the previous schematics. Then we do multiplication, and multiplication is nice and easy in binary because when the multiplier bit is 0 you just write out zeros, and when it's 1 you just write out the multiplicand. You shift them along and add your partial products as exactly the same as you would do previously, and you will have a multiplier. We do multiplication in hardware using AND gates, so AND gates obviously implement that multiplication truth table. So if you think about it, so 0 times 0 gives me 0, 0 times 1 gives me 0, 1 times 0 gives me 0, and 1 times 1 gives me 1. So look at that AND gate truth table and you'll see it's doing bit multiplication. So what else do I need? Well, I need to sum up those partial products, so I need an adder, and I need to shift those partial products along so that they are in the right position. So shifting, exactly the same as we did rotation in the previous lab. You can do that nice and easy using buffers. So if you've got a fixed shift, all you need is a buffer circuit as shown here. So it's implementing a fixed shift by wires. We can then test that one, so again download it, and so you can see again, here we've got the values coming in from the test bench, so 2 times 2 equals 4 on the output there. And we can run that through the virtual bug trap, and again do make sure you're happy why 7 times 7 is 61. As mentioned in the tech support sessions, we have now looked at all the hardware components we need to build our processor. So we looked at the registers this week, the ALU, the multiplexers, control logics, encoders, decoders. So now over the next series of labs and lectures we'll pull those all together, look at the instruction set we'll be designing for the processor, and make our processor and execute some programs. Finally, as always, we have the weekly workshop or exercise sheet. So within that we've got a series of flip-flop based problems. That's the best way I describe those ones, just to ensure that you understand how these D-type flip-flops do work, so the relationship between our data in, our clock and our clear by looking at them connected in different ways. So a key thing to remember about your flip-flops is that they update on the rising edge of a clock. So these flip-flops here will all update at the same time because they are connected to the same clock. So whatever's on their D input is passed to their Q output at exactly the same time. A variation on a ring counter we looked at in the lecture. Got a little extra NOT gate in there. Can you work out what it does? And this one should be familiar. You should recognize what this input circuit does. Remember, this is effectively implementing a 2-bit register. So we've got 2 flip-flops in parallel, and we've got some logic driving it, and that logic is based on the previous output. Then we dip our toe into the land of instructions. So you can see here we're starting to think about how we'll actually represent stuff inside our processor. So if we've got so many instructions, how can we encode that? How can we represent that? So what range of values will these different encodings allow me to represent? And a little bit in 2's complement. Again, can be confusing if you haven't done it before, so as always do give us a shout if you're confused about 2's complement. Then we move on to our robot Cockroach. So this is where we kind of look at a real world context of these techniques and where they're used. So again, we're kind of looking at some logic for encoding and decoding. So we're looking at some control rules to move our robot around its environment and how those should be designed. Finally, we're looking at linkage now into the open assessment. So this is the last week where we look at hardware focused stuff. So at the end of this week, we have looked at all the hardware components that will be used to build our processor. So the next step is obviously to take those and build our processor. And what we're going to do over the remaining lectures is look at how we design the instruction set of our processor, and how we can use these hardware components to build the underlying architecture to execute these instructions and then write programs to solve specific tasks. Okay, I think that's where I'll leave it there, and just a reminder, as I said at the bottom there, if you haven't already had a look at the Simple CPU documentation, then go to that webpage and have a look at it. And if you'd like to look at the processor you'll be using in the open assessment, that is the Simple CPU version 1D, and all its material again is available on that webpage, so do have a look if you're interested.